Welcome back students to the video lecture series. I am Adil Mansoori from Civil Engineering Department of LJ Institute of Engineering and Technology. So in the previous video, we discussed regarding the steps of the rapid sand filter design, right? So in this video, we will start with the numerical related to it, and we will also see regarding the disinfection processes. Okay, so let us start with the numerical. Example says, design a rapid sand filter unit for supplying 10 mld of water. And we just need to design only filter units. Okay. So, let us start with the solution. So, water required per day is given as 10 mld, that is 10 million liters. Right. Now, assuming 3% of filter water will be used for washing of filter. So, whatever the water that is being filtered in the water treatment plant, out of that 3% will be used for washing of filters. Right. So, can we say that total filtered water per day will be 3 times more than the actual filter, right? So total filter will be 1.03, right? So total required will be 1.03 into 10, that is equals to 10.3 mld. Okay. Now, assuming 30 minutes are lost every day in backwashing, we saw that filter gets clogged, right, because of the sand particles. So we need to backwash it, right? So every day 30 minutes are lost in backwashing, right? So how much time out of 24 hours the filtration will be carried out? For only 23.5 hours, right? So the quantity of filtered water required per day, per hour will be 10.30 mld divided by 24 minus 0.5, that is 23.5 hours. Okay, so that comes out to be equals to 0.438 million liter per hour. Okay, now assuming the rate of filtration as 5000 liter per hour per meter square. Okay, so how much area will be required is 4.438 into 10 to the power 6, right, divided by 24 minus 0.5, and that comes out to be equals to 87.6 meter square. Okay, now how many number of units required? So that is the formula, under root of q by 4.69, right? And under root of 438, here q is in kiloliters, right? So in the previous slide I showed 0.438, right? So here in kiloliters that will be 438 divided by 4.69, so that comes out to be equals to 4.46. Okay, so number of units required cannot be in decimal, right? So either we can go plus 1 or minus 1, but since particular value is required, we cannot reduce it, right? So we have to go extra, right? So number of units required will be 5, say for example, and area of each unit will be 87.6 by 5, that comes out to be 17.52, right? Now in the design criteria, I had told you that we need to assume L by B ratio, right? And for example, here we are taking it as 1.3, right? So 1.3 B into B will be equals to 17.52, right? So B will be equals to 3.67, right? Now finding out length, that will be 3.67 into 1.3, that is equals to 4.771, that is approximately 4.8. Okay, so we have to provide 1 unit extra, fine, for standby purpose, right? So in case if any of the units are not working, then the standby unit can be taken into working condition, right? So provide 6 total units of length 4.8 meter and 3.7 meter of width. Okay, so this is how we design number of units required for the rapid sand filter. Okay, so let us now move ahead. So our next topic is disinfection. Okay, so my dear students, The water which is coming out of the filter, either slow sand filter or rapid sand filter, may contain some bacteria and other microorganisms. Right? Now, some of these may be pathogenic. These harmful microorganisms, which are known as pathogens, must be killed in order to make water safe for drinking. Right? Now, complete sterilization of water is not required to make water safe, because the complete sterilization will be uneconomical for large scale public supply. Right? Now, what do we mean by sterilization? So, sterilization means killing of all microorganisms present in the water. Okay. Now, while disinfection means killing only harmful microorganisms, which are known as pathogens, right? And disinfection is enough for making water safe for drinking. Now, disinfection is very important part of water treatment, because the bacterially contaminated water may lead to spread of various diseases and their epidemics. The presence of turbidity, color, or minerals may not be dangerous, though they are harmful but not be dangerous. But the presence of even a single harmful microorganism will definitely prove dangerous to human health, thereby making disinfection the most important process of the water treatment. Now, during emergencies, when complete treatment, including sedimentation, filtration, and so on, cannot be given, only treatment done is disinfection, right? And disinfection is the final treatment after filtration. Now, the aim of the disinfection is not only to remove the bacteria or microorganisms present at the time of treatment, but also to ensure killing of the bacteria that may enter into the water during distribution of the water. Okay, so the chemical used for disinfection is called disinfectant, right? And chlorine is the most commonly used disinfection for water treatment. So much so that disinfection is also sometimes called as chlorination. Okay. Now, you may have a question in your mind. How should a disinfectant be? Okay. So the disinfectant should be effective in killing the microorganisms which are potentially present in water within the contact time available. Okay, it should be easily available and economical. Then it should be safe to handle, and its method of application should be simple. Now, after its application, the water should not become toxic and objectionable to the users. Right? It should be of such a nature that their strength or concentration in the treated water can be quickly determined. Okay? And it should have ability to persist in residual concentration so as to safeguard against recontamination. Okay, so these are the points which good disinfection should have. Okay, now let us talk about different methods of disinfection. Right, so basically disinfection is classified into two parts, that is physical and chemical. Right, so physical processes include boiling, UV rays, whereas chemical processes include halogens, silver and copper ions. Okay, so in physical methods, you can see that disinfection by heat, that is by boiling of water, which is usually done in every house. Though today it is not practiced, the reason is now there are filters which are known as aquaguard or reverse osmosis system are available in every house. But for those who do not have these kind of filters, then they still go for boiling. right? Now, second is disinfection by UV rays, right? And the third, let us talk about chemical method. So, chemical methods include oxidizing chemicals like the halogen. Like we know that in chemistry we studied about the periodic table. The last column was for the halogens, right? Like chlorine, bromine, iodine, and so on, right? Then the second is ozone. Ozone means it is the O3 molecule, right? And other oxidants like potassium permanganate and hydrogen peroxide is also used, right? Talking about the silver and the copper ion, then silver ions are bactericidal, right? Though they are neither viricidal nor cysticidal. Okay, and then there is the last one, that is alkali and acids. So microorganisms can survive in a specific pH range. Okay, that is usually 6.5 pH to 7.5 pH, and they cannot survive in too high alkaline nature and too high acidic environment or nature, right? So as I said, they cannot survive in too alkaline or highly acidic condition. So when lime is added to water, it can kill the microorganisms due to creation of alkaline condition. Right? So out of the various methods mentioned above for disinfection, chlorination is most commonly adopted. So other methods are considered as minor methods of disinfection. Okay. So let us talk about the minor methods of disinfection, that is boiling of water, treatment with lime, excess lime, treatment with ozone, treatment with iodine and bromine, treatment with UV, treatment with KMNO4, that is potassium permanganate, and electrocatalytic process. So talking about boiling of water, the bacteria present in water can be destroyed by boiling it for a longer period of time, right? It is an effective method of disinfection, but it is not practically possible to boil huge amount of public water supplies, right? Millions of liters cannot be boiled on a daily basis for a public supply, right? Moreover, it can only kill the existing germs but cannot take care of the future possible contamination. That is, even though you have boiled the water and supplied the community, for say for example, but at the like distribution point there may not be any kind of contamination, but the pipeline network is very long, right? So there is a chance that water may get contaminated, so boiling may become ineffective, right? So this method is hence not used for disinfecting public supplies. Right? Talking about the XX lime. Lime is generally used at a water purification plant for softening, right? That is reducing the hardness. Now, what is hardness? If the water is hard, then foam forming capacity of water is less, right? So, hard water will not create sufficient amount of foam when added to soap, right? So, it has been found that if excess lime is added to the water, then it can kill the bacteria also, right? And so much so that an addition of 14 to 43 ppm of excess lime has been found to be removing the bacterial load by 99.3 to 100% from even the highly polluted waters, right? So this was about the excess lime. If I talk about the ozone, then ozone gas is a faintly blue gas of pungent odor, right? And is an excellent disinfection. Now, ozone gas is nothing but an unstable allotropic form of oxygen, right? With each of its molecule containing three oxygen atoms. As I said earlier, that ozone is nothing but O3 molecule, right? Now, because of its instability, ozone readily breaks down into normal oxygen and releases nascent oxygen, and the nascent oxygen so produced is a powerful oxidizing agent and removes the organic matter as well as the bacteria from the water. Right? Next is iodine and bromine. So, the treatment with iodine and bromine, that is the addition of iodine and bromine to water, can help in killing the pathogenic bacteria and thereby disinfecting the same. Right? And the quantity of these disinfectants may be limited to 8 ppm, and a contact period of 5 minutes is generally enough. Right? So this was regarding iodine and bromine. So let us start with the next one, that is treatment with UV rays, right? So sterilization with ultraviolet rays does not impart any additional taste or odor to the water as no chemicals are added, but it is very costly, right? And needs technical knowledge and possesses possibility of interruption due to failure of electricity. So this method is unsuitable for treating large scale public supplies. Okay. Next is treatment with KMNO4. This is used as a popular disinfectant for disinfecting well water supplies in villages which are generally contaminated with lesser amount of bacteria. Next is treatment with silver, or it is also known as electric acetylene process. Okay. In this method of disinfection, metallic silver are introduced into water by passing it through a tube. Okay, so water gets disinfected. Okay, let us now move ahead with the next topic, that is types of chlorination. Okay, so there are various types of chlorination. First one is known as plain chlorination, then pre-chlorination, then post-chlorination, then double chlorination, then superchlorination, then dechlorination. Okay. So what do you mean by plain chlorination? So this term is used to indicate that only chlorine treatment and no other treatment is being given to the raw material, or that is raw water. Right? Under plain chlorination, therefore, raw water is fed into the distribution system, right, after giving chlorine treatment only. Okay, and this helps in removing bacteria, organic matter, and color from the raw water. Right? Next is pre-chlorination. So pre-chlorination is the process of applying chlorine to the water before filtration or sometimes before sedimentation and coagulation. Right? And it helps in improving coagulation and reduces the loads on the further processes like filtration. Generally, doses required are high as 5 to 10 milligrams per liter. Okay. Next is post-chlorination. So post-chlorination, or sometimes which is known as just chlorination, is normal standard process of applying chlorine in the end. Okay, when all other treatments have been completed, while treating normal public supplies, the post chlorination is adopted after filtration and before the water enters the distribution system. Okay, then comes the double chlorination. So the term double chlorination is used to indicate that the water has been chlorinated twice. Okay, and the pre-chlorination and the post-chlorination are generally used in double chlorination. Now, post-chlorination, however, is generally used while the pre-chlorination is used when the water are highly turbid and contaminated. Okay. Then talking about superchlorination. So superchlorination is a term which indicates the addition of excessive amount of chlorine, that is 5 to 15 milligrams per liter, and this may be required in some special cases of highly polluted water or during the epidemic of waterborne diseases. Okay, so say for example, if there in any area there are any waterborne diseases like cholera, jaundice, or so on, then you can go for superchlorination, right? And dechlorination. Last one is the dechlorination. So as the dechlorination means removing of the chlorine from the water. And this is generally practiced when superchlorination is done. Okay, so this was regarding different types of chlorination. Okay, so let us now move ahead. So our next topic is breakpoint chlorination. You can see the graph, right? So here the graph is of residual chlorine in milligram per liter versus applied chlorine in milligram per liter. Okay. So what do you mean by breakpoint chlorination? So breakpoint chlorination represents that much dose of chlorine beyond which any further addition of chlorine will appear as free residual chlorine. Okay, so if the water is pure, right, which has no chlorine demand, then any chlorine that you will add will be residual chlorine. Okay, right? You can see this with in the figure, which is shown by line A, a straight dotted line A. Okay, but in case of water containing organic matters and other impurities, as chlorine is added, readily oxidizable substances such as Fe2 plus, that is iron, then manganese ion, that is Mn2 plus, then hydrogen sulfide and other organic matter reacts with the chlorine and reduces most of it to the chloride ion. Okay. Now, after meeting this immediate demand, the added chlorine continues to react with ammonia to form chloramines between point A and B. Okay, and for mole ratios of water, for mole ratio for mole ratios of chlorine to ammonia less than 1, monochloroamine and dichloramine will be formed. Now the distribution of, so after meeting this demand, that is the immediate demand, the added chlorine continues to react with ammonia to form chloramines between point A and point B. For mole ratios of chlorine to ammonia less than 1, monochloramine and dichloramine will be formed, and the distribution of these two forms is governed by their rates of formation, which is dependent on the pH and temperature. Okay. Talking about point B and C, some chloramines will be converted to nitrogen trichloride, that is NCl3. The remaining chloramines will be oxidized to nitrous oxide, that is N2O, and nitrogen. And the chlorine will reduce to chloride ion. Now, with continued addition of chlorine, most of the chloramines will be oxidized at the point C, which is called breakpoint chlorine, right? Which is called breakpoint. Now, continued addition of chlorine after this breakpoint will result in directly proportional increase in its free availability, that is unreacted hypochlorite. Okay. Now, the breakpoint chlorination of water may be defined as the point on the applied residual chlorine curve beyond which all or nearly all the chlorine applied appears as free residual chlorine. The breakpoint chlorination has practical significance since the application of chlorine at or slightly higher than breakpoint concentration will have different advantages. Okay, so talking about the advantages, first one, it will remove taste and odor. Second, it will have adequate chlorine residual. Third, it will complete the oxidation of ammonia and other compounds. Fourth, it will remove color due to organic matter by about 30%. The breakpoint stage should be determined in the laboratory. Next, the breakpoint stage is represented by instantaneous yellow color of the orthotolidine test, right? And generally, breakpoint lies between 3 to 7 milligram per liter of chlorine dose, though it is greatly influenced by the quantity of free ammonia present in the water. Okay, so this is what breakpoint chlorination is. So that's it for today's session. We will continue with some new topics in the next video.